So we know that modeling convection is difficult. We know that trying to understand how heat transfer occurs inside of a liquid is difficult because the standard mathematical machinery of the heat equation doesn't really give us information about what happens when I have thermal energy that's in motion, not because of temperature differences, but because of the motion of the matter that contains that thermal energy itself. And so the goal of what we want to do when it comes to convection isn't necessarily to understand how heat transfer happens inside of a liquid. What we want to do is we want to try to see if we can understand how we can use the relationships that we've developed already to model heat transfer that happens between a solid and a liquid, and then see if we can't find expressions for H that are derived from experiment or empirical correlation, and how those relationships are connected to the geometric and material properties of the objects that we want to study. And so one of the first systems that we should consider studying when it comes to understanding convection is the notion of flow past a flat plate. Now, I don't necessarily want to talk about heat transfer just yet, because the first thing that we have to do in order to be able to understand the heat transfer that's happening in the system is to understand the fluid mechanics. Why that? Why that? Why do we care about the fluid mechanics if this is a heat transfer course? Well, remember what we had talked about forced convection. Right? We had talked about this idea that the kinetic energy of an object or system is connected to its thermal energy, and if it's free convection, vice versa, if it's forced convection, not. And so let's imagine that we have a system where all that we're doing is we're considering this kind of imposed external flow, which is a uniform flow with a speed of u infinity, which you can imagine maybe is being powered by some kind of propeller, right? Doesn't really matter. Maybe there's some sort of fan that's pushing air, and that airflow seems to be some kind of uniform flow where all of the little pieces of liquid are moving in this direction at some speed u infinity. Now that changes as this flow hits this flat plate. So we place a flat plate or something that looks, enough like a flat plate in the path of this fan. And so you can imagine that the presence of this plate will change the way that the air driven by this fan will move, right? And so what we want to do is we want to try and study how does this flow change, and how do we derive specific important qualities about that flow as a function of the properties of the liquid and the speed that the fan is propelling the liquid to, and say the length of the plate, right, potentially, or also where you are on the plate. We might want to study things that happen at specific locations on the plate. So what are the properties in play here? Well, the length of the plate, that's easy enough. The free stream velocity, or the velocity of the liquid far away from the plate, right? The velocity at which the liquid is being forced to flow into the plate. We have a familiar material property, which is the density, the mass density. But then we have an unfamiliar material property here called the viscosity, or more precisely, the dynamic viscosity. Now, the dynamic viscosity is supposed to be a measure that tells you something about the frictional forces that happen inside of a liquid. So, for example, you can imagine that if you have two pieces of liquid and they're flowing at different speeds and they're next to each other, you can imagine that that difference in the speeds causes some kind of force or stress inside of the liquid. If you're not super familiar with the notion of stress, that's fine. All that you should know is that the viscosity is a proportionality factor that relates the frictional force per unit area that impacts a little piece of fluid that's next to another piece of fluid. It relates that force per unit area to the rate of change, or the gradient of that velocity, right, around a specific region of the flow. And so it's very, very similar to the thermal conductivity. Like just how the thermal conductivity is a proportionality factor that relates thermal gradients and heat transfer rates, the dynamic viscosity is something that relates stresses, right, the transferring of kinetic energy. It relates it to a proportionality to the velocity gradients, all right? And so we don't have to worry about that, right? So there's a reason I haven't been writing down equations. It's because we don't actually have to work with that. What we do have to know is that that viscosity, that dynamic viscosity, absolutely matters from the perspective of trying to understand how this liquid flows. And it also is important to write down what the units of the dynamic viscosity are. And it turns out that they're actually quite simple. It's just kilograms per meter second. All right? This will matter a lot later on. So we have this set of properties. What does the flow qualitatively look like? Well, one of the things that's going to happen is that we're going to observe that the flow speed of the liquid, when it gets really, really close to this static flat plate, right? This plate isn't moving around, it's just standing still. The speed of this liquid is going to go very, very close to zero when you are close to the plate. And the reason for this is actually not even that physical, it's mostly mathematical. I mean, if you think about it, what is the speed of a liquid? The speed of a liquid, the thing that we measure, is just the collective average of the speed of the molecules that we are measuring in our device, right? So if I were to try to measure what the average speed of the flow was in this tiny region, even if that region is super, super tiny, there's a bunch of molecules inside of there. And so what we're really grabbing when we capture the flow speed at a specific point is we're actually capturing the average speed of the molecules around that point. If I try to make a measurement that's close enough to the surface, then of course I should expect that that average is going to include a bunch of molecules and particles that belong to the solid surface that are not moving. And so as a result, we expect that the flow speed, right, the thing that we call the flow speed of a liquid, drops to the speed of the object that it's in contact with as we get closer and closer to the object. And that property is called the no-slip condition, okay? And so this is more mathematical. It stems more from how we define the speed of a liquid than it has to do with any kind of like physical interesting property, okay? And so what that means is that as this liquid hits the plate, the speed of that flow is going to become effectively zero, at least on the plate, all right? And what that will do is that it will cause a velocity gradient, right? Because the speed has to go from, zero here at the plate all the way up to the kind of unperturbed background speed that is caused by the propeller or whatever, u infinity, as we go further and further up, okay? As we move, I guess I could write in the y direction. And so what we actually expect to see is that there is this kind of sharp increase of the speed that happens as you move further and further up from, or further and further away from the flat plate. In short, what we are creating, or what is happening, is the construction of a boundary layer, or a velocity boundary layer. And the reason for that is just the fact that, well, we know that there's a very large region past the plate where the flow has a speed that's very close to, u infinity. And we know that there's a region over which this kind of speed drops all the way down to zero. That happens, very, very close to the surface of the plate. And so this is sort of the flow pattern that we observe. Qualitatively, that's just what we see. One interesting thing that happens is that as we go further and further along the plate, we find that the thickness, the effective thickness of that boundary layer grows, right? So it takes longer as we move further and further down the plate. It takes longer for that speed to eventually start to get close to this. And there are many different ways that we can describe the thickness of a boundary layer, and these illustrations are certainly not very good. But you can imagine that if, however we define the thickness of a boundary layer, however we define how large this transition region from zero to u infinity is, that region gets larger and larger as we move further down the plate. And we can only explain that via fluid mechanics. It's not really the point of this course to try to explain it using equations or models. All right? All we want to do is to try to understand the flow. And so you can imagine that if we wanted to plot the thermal boundary layer thickness, we would get something that grows as we go further and further away from the leading edge of the flat plate. Something else that's very interesting happens, though, and it only happens in certain situations and for certain geometries. One thing that is very interesting that occurs inside of fluid mechanical systems, and this doesn't just happen for flow past flat plates, it happens for a bunch of them, is that, if the plate is long enough, for a while, you can imagine that the flow, will look a little bit like this, with the thermal boundary, the velocity boundary layer increasing. But what eventually starts to happen is that you reach a point, if the plate is long enough, where you experimentally start to observe that even though this flow is nice and orderly, right? The fan this is a hypothetical fan that's creating a perfectly uniform flow. And even if the flow at the front part of the plate looks nice, what eventually starts to happen is that you see this kind of very chaotic, unsteady formation of whirls that changes over time and is wholly unpredictable. Okay? And that's even if this is, a perfect fan. And this phenomenon is called turbulence. And this creates a problem because very often what we do is that we assume that a system is in steady state. We give boundary conditions and things like that make us think, oh yeah, the system is in steady state. The boundary conditions are in steady state, so the system should be in steady state, right? Like we should find a solution for it. But we find that even if we have steady conditions, we have unpredictable, unsteady behavior for the dynamics of the fluid past a certain point in the plate. Okay? And now the key thing that I want to do is to talk about how we know whether or not that happens. Is there a way for us to be able to find under which conditions this turbulence generates? Like, how does it depend on the density? How does it depend on the dynamic viscosity? How does it depend on the background speed and on the plate length, if it depends on the plate length? So just to remind you before we get into the math, the idea is that for certain conditions, we find that there's a critical location on the plate at which we observe that the flow transitions from being what is usually referred to as laminar, which is just a flow where it's just like nice and steady, right? Initial steady conditions lead to steady flow. It transitions from this kind of nice laminar flow into this complex turbulent flow. And so how do we know whether or not that takes place? Well, here's an idea for an experiment, right? We're gonna have to do this via experiment. There's no way for us to know this based off of first principles, but there is still a way for us to be clever about it, right? Because we could try to imagine that whether or not turbulence occurs is a function of the different parameters inside of my system. Right? Those parameters are the length of the plate, the background speed, and the mass density and the dynamic viscosity. And so if I wanted to try to create an experiment that told me what this was, I'd have to control for 4 separate parameters to be able to actually pinpoint what or whether or not the turbulence occurs. Okay, which is the goal. But can we make an experiment such that this sort of thing becomes much more simple? Consider the following. Imagine that you put a little weather vane, like right here, just like a little, flap of paper or plastic that's attached to a pin, maybe glued to a wall, or self-propelling. This is just a thought experiment, so it doesn't really matter. But the point is that you just have this little freely flapping piece of of paper or plastic or whatever, that's just there. And depending on where I put it, if the flow is steady and laminar, then I wouldn't expect this thing to kind of be, you know, flopping around. But if the flow becomes turbulent, then I do expect this thing to kind of like whirl around and rotate. And then maybe I have some kind of camera or detector that's taking a look at this little vein. And once it starts to rotate, it will flash a light that says, yes, there is turbulence here. So what we can create is we can define the notion of a turbulence index, which is the output of an experiment that is just 0 or 1, on or off, that tells us whether or not this thing is flapping around, right? It's the output of a camera that's using some kind of algorithm to detect whether or not this thing is flopping around, and by extension, whether or not the flow at that specific location is steady or turbulent. Okay? So this is just a number. This is just a 0 or a 1, right? It's a yes or a no. There's no dimensions attached to this thing. And so if I want to create a mathematical equation that tells me whether or not I observe turbulence at a given location on the plate, then I shouldn't be looking at something that is a function of just, you know, individually these things, or L, right? I shouldn't be looking for something like this, because remember that if this doesn't have any units, I need to create a function of something that doesn't have any units either in order to be able to get the answer that I want, right? In order for this statement, so for this hypothetical empirical construction to be dimensionally consistent. And so if this is the case, then how do we do it? Well, we have to find some dimensional deconstruction of these parameters such that I can generate some dimensionless combination of these things that will have, you know, those appropriate dimensionless matching properties to this. And that would then it will be a function of that, or it'll be a function of those things, right? Because there could be more than one. Now, if we are creating this experiment in such a way where I manipulate where I put the vein, right, then it doesn't actually matter what the length of the plate is. The x is the thing that matters, right? Because if we observe turbulence or not is going to depend on where we put the little vein, okay? So these are the parameters that we have available to us. We don't necessarily care about the length of the plate, not because it doesn't matter, but only because of the fact that we can effectively alter the, you know, the length of the plate that this thing sees by moving this thing forward or backward. So is there a way to construct a dimensionless parameter out of these things? And the answer is yes, and there's only one way to do it, okay? And the way that we do it is, well, let's suppose, pardon me, let's consider the density. Okay, the density has units of kilograms per meter cubed. I want to multiply or divide the density by stuff that's over here in order to start getting rid of these annoying units. So what can I do? Well, maybe I want to get rid of the kilogram, right? But then this has units of meters per second, and this has units of meters. And just like before, this is units of kilograms per meter cubed, and this has units of kilogram per meter second. And so the only way that I'm able to actually get rid of this kilogram is by dividing by the dynamic viscosity. And if I do that, right, then I get m times s divided by m cubed. Oh, pardon me. Divided by kilogram. Both of these things cancel out as expected, and what we're left with is seconds per meter squared. So that's the units of this little dimensional combination. So let's say that we want to get rid of the seconds. Well, why don't we multiply by the speed? Right? That's the only quantity that's left that has units of seconds anywhere, even if it is a 1 over a second, right? So we multiply by that background speed, cancels the seconds, and then we're left with something that has units of 1 over meter. And so, of course, we multiply by the x. And so this is a quantity that doesn't have units, all right? And so rather than saying that this turbulence index, this indicator that turbulence is occurring in our system, is a function of all four of these things separately, it has to be a function of just that one thing that I wrote down. It has to be a function of this product. And this thing right here, this dimensionless combination, is very commonly referred to by fluid mechanicians as a Reynolds number. Okay, so the same way that we created that dimensionless combination that we called the BO number, now we have another dimensionless combination that helps us understand whether or not turbulence occurs in our system, or where that turbulence occurs in our system. And we know that it has to be exclusively a function of the Reynolds number. Okay? And we can try to create physical interpretations of what the Reynolds number is, but really I don't think that that's that productive. That's a very easy way to mislead you into thinking that we know more about these systems than we actually do. The idea is to just think of the Reynolds number as being the only dimensionless parameter that will tell us what any other dimensionless output of an experiment will be, or what it will be a function of for a system like this, right? So we can imagine some other dimensionless output of an experiment that we perform on this system, and then that output can only be a function of the Reynolds number. And so the question is, if we know that the turbulence index is a function of the Reynolds number, what is that function, right? And technically speaking, that function is just a 0 to 1, right? Like we know that the value of the turbulence index switches from 0 to 1, right? Indicating that for some Reynolds numbers, turbulence doesn't occur, and for some other Reynolds numbers, turbulence does occur. It's very simple. And empirically, right, like now it's up to experiment. Now we check the Reynolds numbers over which we observe the turbulence to occur, and we find that the transition to turbulence, at least in flow past flat plates, okay, so for this specific kind of system, we find that this occurs roughly at a Reynolds number of 5 times 10 to the 5 or 500,000. Okay, so if you increase the distance at which you are measuring, the properties of the flow, if you increase the distance of your vane to the leading edge of the flat plate, past a specific point, your Reynolds number is going to increase past 5 times 10 to the 5, assuming that your plate is long enough. And so if you go to that point, you'll see that the flow transitions from laminar to turbulence, and this is just a way to try to understand what it is. And you might ask yourself, well, okay, how does that help me figure out this location? How does that help me figure out if turbulence, like where the turbulence is going to trigger? Well, that's simple. You just say, well, if we know that this is the Reynolds number, and assuming that you know the density and the dynamic viscosity of the liquid and the background speed, all you have to do is just solve for this equation, where now you simply set the Reynolds number to be 5 times 10 to the 5, and then you solve for this critical value of x. Okay? Assuming that you know everything here except that x value, you can find at what distance from the leading edge of the flat plate the turbulence occurs. And you can replace this x with the length of the whole plate to try to see whether or not the Reynolds number actually even ever gets larger than 5 times 10 to the 5. Because if the plate is not long enough to trigger, this 5 times 10 to the 5 transition, then the flow is laminar over the entire plate, right? And so you may be asking yourself, why on earth are we bothering to try to study this? This all seems like it's fluid mechanics, and it is. But once again, the idea is that the way that this system behaves, the fact that the flow changes in specific regions of this plate depending on this kind of Reynolds number criteria, affects the way that heat is transferred from the plate out into the liquid. And so we need to be able to understand these fluid mechanical parameters and this particular transition in order to be able to understand how we can model heat transfer that happens from the plate to the liquid, which we will do in the next section.